Hello, Karen, Cynthia, and whoever else has decided to watch this for no reason. Look at these surroundings. There's nothing really that stands out now, is there, except maybe some lights off in the background. But now, take a look at that. All of a sudden, these three nice little strips on the side of this telephone pole, well, they're clear as day. You can see them without any problem, even though this entire shot is only being lit up by a teeny tiny little LED right next to the camera lens on the phone that I'm filming this with, or that Samson is filming this with. How are these three things so bright compared to everything around them? Well, that's because these are retroreflectors. Retro meaning a thing from the 1970s. Pardon me. Sorry. Retro meaning backwards, and reflector meaning reflector. That means that when light hits these three strips, it will always reflect back towards the camera or towards the light source. And they work from any angle. You can be standing over there, or anywhere really. But how on earth do these three things, well, one thing, work? And how are they so gosh darn bright? Mesmerizing. When light hits normal objects, it reflects in all directions. This is how we see just normal things. However, when light, like say the light from this laser, hits a mirror, it only reflects in one direction. The angle at which the light reflects is equal to the angle at which it attacks the mirror. If we add a second mirror at a 90-degree angle to the first one, showing that, hopefully you can see it, when we can shine our laser light at it and get a beam that reflects back in what looks like a parallel line back to the source of the light. That's great, isn't it? Does that mean that we've made a retroreflector? Well, no. Because you see, this only works if we only move our light source in two dimensions. Like this and like this. Side to side, back and forth. As soon as you move the light source up and down, we're no longer getting any reflection at all. The beam, the returning beam, is no longer parallel. However, this problem that we have with only two mirrors is not difficult to solve at all. We solve it by adding a third mirror, which is at a 90-degree angle to both of our two existing mirrors. Now we have what is called a corner cube of mirrors, because it is the corner of a cube. Now, when we shine our laser at the mirrors, it will always come back in a parallel line to our original beam of light created by our source here. You can see, I am able to move it all over the place on this reflector, and it is always coming back at a parallel line. As we showed in the demonstration outside, when light hits off a single mirror, such as this mirror panel, three-dimensional drawing, it goes back. It will always reflect off the surface of the mirror from the same angle it came. The angle of attack right here, is equal to the angle of reflection, just like that. So if it attacks the mirror at 30 degrees, it's going to leave the mirror at 30 degrees, right? Now, we can use this property to determine how this worked with two mirrors, because outside in the demonstration, it did technically work with just two mirrors. You can see, if I can position this just right with the camera, you can see that when I move side to side like this, you can just about see the camera in the same place at the division between the two mirrors. even when I move it forward and back. However, up and down, oh, nope, it's gone. You can't do it. It only works in 2 dimensions. However, we can prove how that works, again, using this very simple rule. If we take our 2 mirrors, right, like this, and have a light source come in like this, hit here at 30 degrees to the surface of the mirror, it will reflect back off at 30 degrees. 30 degrees, right, like that. Now, we know that this here is a right angle. We've positioned them such that these 2 mirrors are at a right angle from each other. So, how do we determine the angle at which this beam of light, this reflected beam of light here, hits the mirror? And therefore, how do we determine what angle it leaves the mirror at? Well, we can do that by making a triangle. If we draw lines like this, right along the surface of the mirror, well, we can see that there's a triangle now in the center. And because these 2 mirrors are at a right angle to each other, we know that this angle here is a right angle. Well, I mean, brilliant. That means that we have a right triangle, and we already know that this angle here is 30 degrees. My drawing skills are very bad. However, you can see that this beam of light here is 30 degrees away from the surface of the mirror here because it is on attack as well. This is 30 degrees. And so, how do we calculate this other angle? Well, the interior angles of a triangle will always be equal to 180 degrees. Hence, 180 minus 90 minus 30 is equal to 60. Therefore, this angle here is 60 degrees, and therefore it leaves the mirror at 60 degrees. Pretty simple, right? But how do we know that this line is parallel to this line? It doesn't look like it because my drawing is very not to scale, but in reality it is. How do we know that? Well, in order for this light to be reflected back parallel in our 2-dimensional space here, remember, it has to be reflected a total of 180 degrees. And it does that here. Well, right here we have 120 degrees. Because this line here is 180. So this line is 120 because we've subtracted 30 degrees from either end. 180 minus 30 minus 30 is 120. This angle here, which is significantly easier to see because it's not quite as poorly drawn, is 60 degrees as well, along with these other 2. How do we know that? Well, because this angle here is 180 degrees, minus 60 is 60. And 120 plus 60 is equal to 180 degrees. This line hit the mirror and came back, hit this mirror, then hit this mirror, then came back out again in a parallel line to the original. However, if you were to say have a line of light that comes in like this and hits the mirror, well, it wouldn't be parallel at the end because it would hit here, reflect about there, and then be reflected down because it already came in at a downward angle. So at each junction, it's going to reflect down more and more. This will be drawn more accurately, be drawn down like that, but it isn't drawn accurately because this is my scribbles, as you can see. So this doesn't work. Now, we proved outside the way we solved this is by adding a 3rd mirror. But we only really proved it in theory. We went outside with a laser and it looked like it was parallel. We need to prove that it is actually parallel. So let's make another drawing, but this time with a 3rd mirror. Here is our 3-mirror drawing. We know that this right here is a right angle, this is a right angle, and this is a right angle. All of these mirrors are at right angles to each other. That's how they're set up. This is the corner of a cube. It's a corner cube, as we can see here. Now, when our beam of light comes in at an angle like this, make it a rather extreme one, you can see that this line isn't just making contact with this in 2 dimensions. It's moving in all 3 dimensions. So if this were to make contact, this beam of line here were to make contact with our only 2 mirrors, well, it wouldn't be reflected parallel, but it is with these 3. You need to figure out why. Now, the first thing we're going to do is, well, we're going to draw the rest of the line. See, this is going to continue to come down the same angle to this one like that. Now, from this perspective, it looks like this hasn't been reflected at all. However, you can see when I draw a line along with the path of the mirror, which in reality bends down a bit like that because of perspective, you can see that it actually has, you can see a little better that it actually has been reflected. Those 2 are the same angle. This is the angle of attack, that's the angle of reflection. Now we've got our angle on this mirror, about right there. You can see follows the path of that. And then it's going to reflect back off this mirror at this angle again. Back off and down onto this mirror. This drawing is not to scale, so take it with a grain of salt. If I had a proper graphing program, I would use that, but no, I just have a whiteboard. So, for simplicity's sake, let's say the original angle of attack here is 30 degrees. We've been working with that number already, so we know that this angle here is 30 degrees. And because we've made another triangle here, well, in fact, we made the same triangle right in here, this angle here we already know is 60 degrees because we've just taken the same triangle from our previous demonstration with 2 mirrors, our previous triangle, and just sort of moved it in a 3rd dimension, right, like this. So then we know that this is 60 as well. This angle, remember this angle is coming off the mirror, it's coming off in a way I can't quite show. This is 120 degrees, and this here is another 60 degrees. Because here we have a 180, and here 180, and here we have a 180. These lines are not intersecting. This line is in front of this angle. So, this is going to come off again at the same angle, just like that. So, how do we prove that these 2 lines, our original angle of attack and their end angle of reflection, are parallel? Well, with these numbers here, we have already shown that if we were to only observe this set of mirrors from 2 dimensions, such 2 dimensions so that this mirror here would be invisible, essentially, viewing them, mirror here, viewing them only from this direction, so just like that, well, it's already made a 180-degree rotation this way. However, we're viewing this in all 3 dimensions, so it has to make one more turn. And that turn has to be another 180 degrees, but viewed from these 2 dimensions. So if you imagine this as the x, this as the z, and this is the y, we have to prove that it makes a 180-degree rotation along the x and y plane and the z and y plane. Now, those 2 share the y, and that's very important, as you'll see shortly here. We can calculate this angle here by making another triangle. You can see that if we draw a line like this and a line like this, we've got a triangle here. These 2 are lines that are straight, even if they don't quite look like they are. They are straight along the surfaces of these 2 mirrors. And so we have another right triangle. Because these 2 triangles are a right angle from each other, we know that this is a right angle right here. And we already know that this is 60 degrees. So what's this one? Well, 180 minus 90 minus 60 is equal to 30. Hence, this here is also equal to 30 degrees. We can then figure out what this angle is, because this is 180, hence this is 180 minus 30 minus 30. The same as this one here. So right here we have 120 degrees. Now we've already calculated that looking only from these 2 axes, the y and the x, we've made a 120 degree rotation. However, we need to make that rotation one more time, just so that it is going, just so that we can see here, it's going parallel here with the original line. Our original line, just so that our end reflected line is equal to our original attack line. And, well, this angle is serving double duty because it is the angle that it is reflected along the y-axis. Hence, it plays a role in determining that this 60 and this 120 is equal to 180. And 120 plus 60 again, because it's the y, we need to make the second rotation along the y and the z-axis. Well, we need to make that rotation again. So, it's 180 degrees in total, both ways. You can see 120 plus 60 is equal to 180. 60 plus 120 is equal to 180. It has made both of the necessary 180-degree turns, and hence we know that this line and this line are parallel. This means that the beam of light that is originally hitting our reflector is bouncing from one mirror to another, and coming back out again in a line that is, again, parallel to the original line here. You can see that, again, in the demonstration footage. It's parallel. And now we've proven that. And now we know how these work as well. These are retroreflectors just like this. The difference is, this is one very, very large retroreflector. These two have a whole bunch of teeny tiny versions of this embedded in them, melted into the plastic that makes up these. That is why the light that we were shining at this was able to go right back to the camera, why these look so incredibly bright. It's because just like how the light that we shone at this reflector was reflected back parallel to our light source, the same thing was happening with these. It's just that you can't quite see the corner cubes inside of these because they are very, very, very small.